Gosh, it's almost time.
Yeah. Yeah, I still see people kind of filing in, which is great.
Have you done this before, Graham?
Yeah, I've been at Whitson about 7 months. I was with Fiquet for 15 years before that.
Okay. Okay.
But yeah, this will be the second kind of webinar I've helped moderator
So,
get going. Yeah.
what is typical attendance on these things?
Um, I'll have to get back to you on that. Like, it's funny. Like a lot of people will attend live, and then sometimes people can't make it, and they'll just watch the recording, the week after, or it's basically available for people to look at whenever they want after as well. Yeah.
No, that's fine. You don't have to do. I don't want to give you any extra work.
Yeah, I'll say it ranges from 70 to 300 people.
Okay.
Yeah. But I have started recording, so I think we'll get going if that's all right.
It's okay with me.
Excellent. So my name is Graham Helfrich with Whitson, and today's webinar, it's going to be RTA, or rate transient analysis without interpretation. And I like this title because it really just leaves you very curious to figure out what does that mean exactly, right? So I'm excited to learn what it's going to mean today. Our speakers today are going to be Larry Lake, Leo Rose, and Mark Walsh. So just some kind of housekeeping here. There's over 150 people actually registered, and I see people are still filing in. All of our audience members are muted because we're going to ask people who have questions, and we want lots of questions to come in, please. There's a chat window in Teams, and you're really encouraged to type any questions or any issues you're having hearing or seeing things. Just type in the chat window, and we'll be able to answer questions at the end, I'm thinking. We've got about up to 60 minutes budgeted here, and this is recorded. So if for some reason you have an obligation you have to jump out to, everyone is going to get a link to the recording to review after. Okay. So this webinar is hosted by Whitson, who I work with. Just a quick bit of background. I think a lot of the people on the call are already Whitson partners. For people who don't know us, a lot of our history has to do with PVT analysis, but in the last few years, there's been 80 operators who've partnered with us for doing modern RTA, web-based reservoir engineering, even nodal analysis. So if you're not a partner, just let me know, and we'd love to talk with you. There's a number of software courses that Whitson offers through the year. You can find the calendar at whitson.com/training. I just delivered a course last week about nodal analysis, optimizing gas lift, avoiding liquid loading, things like that. But these are all recorded, so if you're a Whitson partner, just a heads up, there's a lot of included training in the past and coming up as well. For people who are really keen on PVT, there's a whole bunch of PVT courses available. Again, complimentary as a Whitson partner. They can be found at this website here. This webinar, like I mentioned, is going to be recorded. Our past webinars are also recorded, so if you're curious about things like choke management for liquid yields, things like that, just go check out whitson.com. You can find past recordings, and this webinar will ultimately be added to this repository as well. So just introducing Larry real quick here. He's a UT professor, and I think you're coming up on 46 years at UT, right, Larry?
Yes, creeping up on.
That's amazing. So I'm not going to be able to do your full bio justice, but really you specialize in reservoir engineering and geochemistry, from what I understand.
Yeah.
You have like more than 100 technical papers and textbooks, and just a ton of publications and contributions to our industry through your career. You have served on the SB board of directors, and again, it would probably take at least 5 or 10 minutes to read your entire contribution to our industry, but I just wanted to leave your full bio here for anyone else who wants to check it out. So, Larry, do you mind if I pass the torch over to you now, and You can share your screen if that's okay.
I think it should be if you switch over. It should be already shared. Can you see it?
Okay, I'm going to stop. Let's see here. I'll let you know.
You got it?
Not yet.
Mm-hmm. Well, I'm afraid to push the share button because it might mess up what I have.
Yeah, I think you'll need to press the share button again, Larry, just because it's not coming up.
Okay. How about that?
Perfect. We see the main slide. That's perfect.
Okay. Good enough?
Yes, sir.
Good. Are we ready to go?
Yeah, I can hear you well. I can see your face and the slide, so I think we're okay.
Okay. Good morning, folks. Thank you, Graham, for the introduction. I was actually expecting you to read my entire resume whenever you introduced me, so I might finish a little short here. Anyhow, my name is Larry Lake. I've been at the University of Texas for more than 40 years. And the technique that we're promoting today, or actually presenting to you, is something called rapid RTA. I've actually spent most of my career in the conventional world. So when I do something like this, it's stepping out for me a bit. And I'll refer back to that experience a couple of times during the presentation. There's a lot of similarities. I mean, there's a lot of differences, but there are a lot of similarities. And that similarity is we're doing what reservoir engineers have done since literally time immemorial. And that is, we're taking a little bit of data, sometimes a lot of data, fitting that sometimes to a model that ranges from simulation to decline curve analysis, and they're extrapolating into the future. There is not, to my knowledge, a priori or a basically first principle simulation of anything in reservoir engineering. And so philosophically, it's the same thing we've always done, but there's a lot of differences too, as you'll see when we go through. So it's rapid RTA. Well, that's just great. How do I go forward, guys? Push the button.
Yeah, you may have to click on the screen where the main slide is.
Yep. Okay.
Okay.
So here we go. This is a slide mainly intended to set the stage for what's coming afterwards. There's a rate on the left-hand side in green over here, and this is time over here in years or days or whatever. You notice the green axis is a logarithmic scale. And here we have this green dots that are oil rate, and it refers to the left axis over here. And the dots over here that are kind of a triangular orange are the bottom hole flowing pressure, and refers to the axis over here. The key thing here is this Q, and the notation is it's a function of time. Time is here, and X is the collection of parameters that have to be adjusted to bring a match. Please note one thing here is there's an initial reservoir pressure that plays a role in these fittings. So this is kind of like the schematic for slides to follow. There's going to be some pretty very busy slides following up, but this will try to follow this notation. So well, yeah. So what happens? This basically is a decline curve, or any sort of curve like this. This is what was on the previous slide. But what happens if the bottom hole pressure changes? You know, we can change out the pump, we can work over the wells, or all sorts of things. But the bottom hole pressure does change, and I have to admit that we've kind of picked this case to exaggerate the effect, because so when the bottom hole pressure goes down from 4,000 to 2,000 psi, of course the rate rises, and it just seems very improbable that a single decline curve model, I forgot to say UP says unit pressure drop, that we'll define that later on, a single decline curve model would be able to fit all of this here and thereby would not be able to be extrapolated to a reasonable answer. And that's the issue that we're going to do with now. There's been times in the past where we didn't seem to have bottom hole pressures very much in reservoir engineering data. But it seems like there are more of this than there have been in the past, and it probably will be, there'll be more and more collection of bottom hole pressure data. Often these things are inferred from surface measurements, but they could also be inferred from downhole measurements. We don't make the distinction in this presentation. So the production rate is a function of reservoir pressure, which in this case has a discontinuous change here. And in the bottom hole flowing pressure, which is there, and to me, surprisingly, the initial reservoir pressure, which is up here. So this is some data. We've done a lot of cases, and I should have mentioned that much of these data were done by Leo, either through his dissertation at the University of Texas, but also significantly while he's been at the Bureau of Economic Geology. And here is a decline curve model history match with tight oil. Once again, green dots are the actual rates, and the dotted red line are the decline curve model. This is the bottom hole flowing pressure here, and you can see the units. This is a fit with the decline curve model. And here is the same thing with bottom hole pressure factored in, and you can see it basically, it's almost an uncanny match. I mean, not only does it match, and I'm looking at the blue curve here, not only does it match in average, but it actually matches in fluctuation, and a lot of those fluctuations are because of the fluctuations here in the bottom hole pressure. The bottom hole pressure, of course, is an input to the process, so we'll see how they fit. So one of the ideas, in fact, one of the main ideas, is to actually take the results and extrapolate those sometimes into the future to see what the future production would be. This evidently is very important in the industry. Many people ask about this all the time, and you can see just based upon the decline curve over here, it doesn't really do very well. But when we're over here with rapid RTA, we reproduce the fluctuations as we said before, and here is the extrapolation. If I compare the blue curve over here with the red curve over here, you can see the prediction is very, very different. Of course, to make the predictions into the future, you have to assume something or know something about the bottom hole pressure, which is here. So we think for accounting for the bottom hole pressure is important for extrapolations. So this has become more a realistic case. This is actual real data, and I have to give a shout out to the SPE for publishing a lot of data on their website, which we've used. And you can see the identification here is data set number 1 and the fifth well. In other words, this is real data. So you can see the bottom hole pressure declines, but actually it goes up here a little bit. That's kind of weird in here. And you can see that the green dots are the oil rates, and the decline rate without bottom hole pressure is fluctuating all over the place. Now, it turns out, well, fluctuations may be real, but probably not, because this is done by fixing the initial reservoir pressure at this value in here, and so it seems to accentuate the fluctuations in the bottom hole pressure and cause these fluctuations in the rates. It basically is so-so match. But part of a rapid RTA is in addition to matching bottom hole pressures, it also gives you an estimate of the initial reservoir pressure. And you see it's a much different case over in here. This matches on average and also on fluctuations. And the bottom hole reservoir pressure has been changed quite a bit. So it incorporates bottom hole pressure, function of time, and then it incorporates an estimate of the initial reservoir pressure. So here's 4 or 5 slides into the presentation. Here's objectives, is to provide a fast and simple approach to incorporate bottom hole pressure. And I'm glad that we underlined those four words in the second line, into any decline curve model. Now, we've always been a little partial here at the university to be a physical-based model. But this is a very clever thing here that Leo did, was that fixed it so that we can put any decline curve model, as you will see. So it will account for inaccurate bottom hole pressures, and I'm sure you've all seen cases in which we've seen the bottom hole pressure rise and the rate go up too, which just is inconsistent. It allows an estimate of the initial reservoir pressure, incorrect reservoir pressure, and then it sorts out bottom hole pressure and rate inconsistencies, which I mentioned a few minutes before. And it, as I hope to convince you, improves the production history matches, and it improves the production forecast from unconventional wells. So, big pause here, catch my breath. And so here's kind of the big picture, as it says at the top of the slide. We will come up with a unit pressure drop rate, QOP, which for this example is an exponential decline. And we then add to it the variable pressure drop and add to it the changes in the initial pressure estimate. And I'm trying not to be too equation-y here, but here we are, the equation is here. This is really a clever thing. Leo had a good idea here when he did this. So let me spend a little time. This is the predicted rate versus time, and the semicolon here separates the parameters from the variable, and he writes that as a function of the difference between initial pressure and the pressure at some time interval times this QAP. The clever thing here is he recognizes that that when we use traditional decline curve analysis, we are, like it or not, assuming the bottom hole pressure is constant. And so he will interpret it, this QAP, as really the ratio of the rate plus the bottom hole pressure, and therefore he can get back the rate. This is no longer a rate by itself. He can get back the rate by just multiplying times the differences in the pressure. Notice he's got a flowing pressure at a given time 1, and he's got the initial pressure here. It is surprising to me that initial pressure plays such a role in this, but maybe not, because it's the first term in this equation. These other terms here are more or less superposition that you've probably seen before, that have the superposition of the unit pressure rate over here. So it's a combination of superposition for the varying pressure. Up here we see the varying pressure changes in steps, but it could be a lot of different changes. And the basically the decline curve rate corrected by this amount here. In my other hat in the conventional world, we've worked with something called capacitance resistance model, which I'm proud enough to claim that we invented at the University of Texas. This has a lot of similarities to that. So like here is the contribution from what went before it, the bottom hole pressure, and here is a contribution from the changes in bottom hole pressure. If you notice, if the bottom hole pressure doesn't change, this term is 0, and we're back to where we are. So there's a lot of similarities between this and QRM. There's a lot of differences too, but this part is the same. So some quick comparisons, and not probably we haven't covered the waterfront with all possible models, and we may have left out somebody's favorite model. But the first column shows the method, and then we're going to ask ourselves, is the procedure fast, robust, accurate, and can it use different models? And here we go. This is standard decline curve analysis: fast, robust, not very accurate, mainly when the pressure changes. And of course, one of the strengths of decline curve analysis is you can use different models. This is traditional RTA: fast, not very, robust, some erratic. In fact, we get the impression that interpreting well takes a lot of trial and error, manual trial and error with people. So we say sometimes robust, sometimes accurate, and can it use different models? We're aware of the fact that some people have used superposition pressure to account for the bottom hole pressure, and in this, that has some strengths. It's fast, it's different, but it also has some problems. We seem to think it has some problems with accuracy and conversion. But the main difference between that line there and rapid RTA is the use of the initial reservoir pressure. And here, this is yes on all these counts. We think typically, and there's demonstrations available at the end of this presentation, typically it's somewhere between 5 to 10 minutes to fit a set of data with minimal human intervention. So let's go through the procedure. Now, this slide is actually reproduced at the bottom of the presentation in the supplemental material, where there are equations that correspond to each of these steps, but I wanted to take those out and just show you what the steps are. You select the decline curve model, you estimate the initial pressure, and the flowing well pressure is given. You history match. Please note we use cumulative production here because it works a little bit better than the rates, but it's the same thing. We had imposed the pressure drop correction like we had in the previous slide, and then we correct for the initial pressure as we had in the previous slide, and we check for convergence. We check for whether CI, the initial pressure, changes from one interval to the next. If it doesn't, we go back there, and if it does, we can make some predictions. It's an iterative procedure, but since everything is automated, it goes by pretty fast and minimal human intervention. So let's move to rates. And this is sort of a physically based model. This shows a horizontal well with a pair of fractures that are planar fractures. And we imagine that the flow is coming from the stimulated volume here into these fractures. And the picture looks something like this. Now, I like this picture because it has a physical base to it. But I have to say two things about it. For one thing, we are using linear coordinates here to solve the equation. You can write this quote down. Unconventional production has freed us from the tyranny of radial coordinates. Yes, it's a good thing. The second thing is, well, let's not get too serious about it, because I have worked with other groups here at the University of Texas that have actually created fractures that you can visualize, and they just don't look at all like this. They're usually branched, they're usually none of them. And so while I like this model, it's probably not exactly what's there. In fact, you can write this down too. What you see, that means to say what you see in the geology, is not what you get. And that is a discouraging finding for someone like me who spent a lot of time walking around outcrops trying to see what the geology looks like. Simpler models tend to do the best. So it's 1D, slightly compressible. And here is the unit pressure drop solution. It has only two variables. Unit pressure drop is here. This is a dimensionless rate. That's time versus, that is scaled by a tau, time constant. And here's the pore volume, compressibility, and the time constant here. And the fitting parameters, and this is one of the reasons why it runs so quickly, is that there's only two parameters to fit. But it does encompass, as I say in my class all the time, there's only three things that reservoir engineers are there for. It is, first of all, to estimate how much, and that's what the VP is. The second thing is how fast, and that's what the time constant is. And the third thing is how, but how's already been settled on this problem because it's unconditional production. So how much, how fast, and how. That's reservoir engineering. Okay, next slide. So first thing you usually do when you're trying a different numerical technique is use a synthetic case. So here is a synthetic case in which there are 1, 2, 3, 4 pressure drops, and each drop has a certain amount of noise in it. Bottom pressure is up to 45%, which causes, obvious signals here in the production. Now, I think if you saw this in your production data, you probably would suspect something like this was happening. But we wanted to make sure we saw an effect. Here's two reservoir initial pressure estimates, the true one and the incorrect one. And the lines here, the blue one is the true bottom hole pressure, which, because this is a synthetic case, we know. So we match the production history, these things here. We match the initial production and pressure, and we match the bottom hole pressure. If I were doing the slide again, I would probably reverse the order of these two things. So here's the way it looks. Well, there's the data that was on the previous slide again. And here are the true versus estimated parameters. True are here, and here estimated, and it's just really good. Really, really good. So less than 2% error. Remember, synthetic, so we expect it to be good. But real cases, well, as I mentioned before, that we can use a variety of decline curve models. Here they are. This is the slightly compressible, one-phase slightly compressible fluid model. And this is a series sum. And really the nicest thing about this, you notice it's the unit pressure drop solution here, is that we don't really have to worry about flow regimes, about boundary dominated or things like that, which means that there's really no need for segmentation of the data. You just play it like it is. So that's the physical-based model, we'll say. Well, the logistic gross model is something that a student here at the University of Texas did several years ago. It's basically a special case of logistic equation, which has been around since the 19th century. And it has three parameters, which you see here. And then finally, the hyperbolic model for ARPS, which is here, which has three parameters too. One of the things that I understand happens a lot is that b-values, when you do this with straight out, you get b-values that are outside of the pressure, outside of the range of 0 to 2. That can lead to odd predictions. So as you will see in what we're doing, we tend to correct that in the case. So here we go, compared results. And now I'm going to go a little faster than I have been. So this is well number 2. And we see the green dots here are the oil rate on the left. Over here, the red dotted lines is the single phase monofit without pressure. And you would say it was sort of okay, but here the pressure is rising again. And that's, the rate's rising again, and that's probably because the pressure starts falling a little faster right down here. And here is the estimated reservoir pressure. Once again, matches even the fluctuations down here and here. So this is the prediction. Now this is the same slide as before, except the scale down here has been compressed to show you what the prediction looks like. And here's the prediction with without the pressure. I have to always look at the caption here to remember what I'm doing. And here's the prediction with the bottom hole pressure. And once again, you have to know something about how the bottom hole pressure is operating in the future to do this. And here are the results. Now, in this case, we have no standard to compare it against. So when I compare one case against the other, I'm basically looking at the effective pressure, not against the truth case. But here are the rapid RTA, here's the rate time, and you can see there's some huge differences down here in time constant, and especially in estimated ultimate recovery, which translates into pretty big differences in recovery factor. So, number two, this is the same thing with the logistic growth model. Please note that this curve, remember green dots are the rate, and the red dashes are the fits. Please note the logistic growth model actually capture this little rise right here at the first, which is pretty interesting. That's true with or without the pressure, but with the pressure correction, it's just incredible. It's just very good in here. And once again, here's what the prediction would look like. Okay. So once again, here are the summary of the comparisons between the two, and let me point out the estimated ultimate recovery rate time versus rapid RTA and rate time only. Big differences. Okay, so and then real quickly, here's the hyperbolic model, the arcs curve. The arcs curve does not capture the initial rise in here, and you might think that that's pretty good fit, but the prediction is not great, or at least it looks not great on this plot. And here are the comparisons. And so here's a quick comparison of all three. Oh, I forgot one thing back here. The dimensions B with the rate time analysis only is 2. That's outside of the acceptable range of what this can be, and that leads to segmentation of the data in practice. But when we correct for the bottom hole pressure, it's back to a very reasonable 0.56. So I can make the claim without a slide that we make better, more reasonable parameter estimations. And here's the comparison of the three. This is with the pressure, this is without the pressure. With pressure means rapid RTA, and there's quite a difference in the estimated EUR, whichever decline curve you use. Now, I have to say that we've talked about the arcs curve, the hyperbolic curve, but whatever your favorite decline curve model is can work here. And I know there's several out there, so any of them would work. Now, I'm going to go into the home stretch here, and I'm going to talk about gas. Now, I'm very much skipping around here because, first of all, it's fairly involved, and second of all, I don't fully understand it myself, but basically, it's very similar to what we did before, except everything has to be changed to pseudo pressures. Here's the forecast with pressure. That's there. Here's the bottom hole pressure down there. And you can see that this is pretty good correction here. Not quite as good as the oil was, but pretty good. But the added benefit here is that you can actually make probabilistic forecasts in here. I love probabilistic forecasts, even if I don't necessarily know how to do them. So let's presume that we have, and at the end of this, in the supplemental material for this presentation, there is a flow chart for how to do the probabilistic forecast. And so I'll show you the differences between things as we did before. And we could have done this with the rate case, but since I have roots back in the conventional world, I'm kind of interested in what the half length would be, and I'm very interested in what the permeability would be. And since we've got tau and we've got the original gas in place, and we use the physical model here to do this, there's a relationship between the two, and so we can estimate these. Now, Here's the estimates, rate time versus pressure time versus pressure rate time. Big differences again. And here's the probabilistic forecast. Please contact Leo or Mark or somebody here to get some details about this, but you see the multiple forecasts here, and it's probabilistic, and we don't quite know how it's going to work, but it is encouraging that the further we get away from the data here, the more the range of uncertainty is, which is obvious here, but actually it's true back here a little bit too. And so my favorite slide is this one, which shows the posterior distribution. And posterior is a fancy word for saying after you've done all the processing, this is what you get. And so here's a distribution. This is a probability density plot, a fracture half length. You can see the P90, which is over here, the P50, which is here, and the P10, which is over here. Pretty good distribution. Pretty good distribution. Most interesting one to me is permeability. And I've looked at this slide a lot, and I've looked at a lot of permeability distributions for conventional reservoirs. And there is a substantial amount of variability here. Of course, the permeability is a lot smaller here. But it seems to me the variability here is smaller than the permeability measurements, core plugs or something, in the conventional measurements. I feel like we should follow up on that some more. And then last but not least, the 20-year EUR. Good plots. So just to wrap it up, that's the slide I showed you earlier, and this is the rapidology at the bottom. We think it overcomes many of the issues with previous techniques. And I'll just finish up with this slide here, which is a screenshot of a web page that Leo has recorded that shows a demonstration with the instruction on how to do it. And he was supported by the STAR program here at the Bureau. And this, of course, is from the University of Texas at Austin. So please, if you're interested in trying it out, do this. And suddenly, fast recourse model that incorporates any decline curve model. Estimates initial reservoir pressure, estimates consistent bottom hole pressures, contains model parameters of future production, and estimates uncertainty if you would adopt the probability approach part of it here. So that's it for me. Acknowledgements for this, and thank you very much. Questions, please.
Thank you very much, Larry. I guess I just wanted to give a chance for our other presenters on the call if they have anything else they want to just chime in with before we answer the questions. Sure. And Matt or Mark, sorry, I think I had temporarily muted you, so heads up.
Yes, Graham, I will start jumping in and say that essentially, if you want to try this method, you refer to the URTEC papers that we have here, but also, as Dr. Lake mentioned, we have a web-based application that mimics, these results, and that is for free, and you can try it with your data, SP data, and you can compare, just decline curve analysis and what we call this decline curve analysis with pressure.
Thank you. Okay. Yes, please.
I'll chime in with something additional, just from a historical perspective. This is Mark Walsh speaking. Our solution to this problem didn't just come upon us when we first started attacking this problem. This problem, we had been looking at it for 2 or 3 years, and we had never come up with a satisfactory solution that was robust and fast. And many of our original attempts were coming out to be 30, 45 minutes per well in order to do everything. And we were finding that disappointingly long. And after looking at it and trying many different solutions that ended up didn't work very fast, Leo, after many failed attempts, finally came upon this one, and we started zeroing into about 45 seconds to 30 seconds per well. And when you think about this, with all the data that you have over several years that you're looking at, and some of the inconsistencies in the data, it was really our conclusion was this is a phenomenal speed improvement to do each well in about 30 to 45 seconds. So based on that, we're very impressed with the speed on this one.
Thank you, Mark. I'll read a couple of the questions, and these are just in the chat window. So if anyone does have any outstanding questions, make sure you type them in the chat window. The first question is, how can we apply this formula for shut-in periods? And he's referring to a formula on slide 8, I believe.
I have to go back to slide 8. Okay.
Sure.
Okay. I think I know what he's talking about. Well, if the effects of shut-in is found in the bottom hole pressure, you just keep going. In fact, I think there was one slide that showed, maybe we should go back. Green, can you do that? Let's see. Oh, there it goes. I hate to go back on the time. That's a long ways back.
Mm-hmm.
But if that is manifest in the bottom hole pressure, then it should just keep going, right? Excuse me. When it flashes through it like this, I remember things I forgot to say.
Yeah.
Okay, I'll get there. Goodness. Yeah. So if the data, if the bottom hole pressure, if the rate, of course, would be shut down. But that should cause the bottom hole pressure to increase, and that effect is captured right there. Now, if it's not captured, of course, it won't work, but you get the idea.
Okay.
Yes,
Thank you.
I'll chime in on that. If you have accurate bottom hole pressure, that's actually showing the bottom hole pressure is going up. The method will when it estimates the rate, will estimate a rate reflective of that pressure.
Okay. The next question, and by the way, Larry, if you want, you can also navigate to the chat page to see this as well, but I'll read this. So it said the question is, to generate the unit pressure drop, I understood that the reservoir and frac parameters are required, including permeability and fracture half length, but we don't know their values until we do RTA. So that was the question.
Yeah, I'm not fully sure I understand that question, but
Yeah, I understand it, Doctor. Can you go back to the slide of the shale gas well with the fracture half length and the permeability estimate? So how you are going to estimate your permeability and fracture half length? You don't need an interpretation as doing a diagnostic plots like a normalized rate versus material ballast time. You know, if you are you can use an empirical model, you won't get those permeability and fracture. But if you are using a analytical or numerical model, a physics-based model, because you are history matching that production, you are going to get your pore volume and your characteristic time or time of end of linear flow, and then you back calculate the permeability and the fracture half length from the pore volume. Can you put the slide of the parameters for the shale gas well, Dr. Mike?
shale gas, well, yeah, okay.
So we are doing the history match. This is an automated, that is why it's RTA without interpretation, because we just put the model and then we do the history match. We estimate these parameters, in this case for this compressible gas model, original gas in place, and also characteristic time. And when we have those parameters, as we history match the well, we back calculate the fracture half length and permeability. So you don't need an interpretation. We are just doing the history match and then back calculate that.
I think I
Right, and
understand
this-
the a little bit better.
This Mark Walsh, I'll just chime in to answer your question very succinctly. No, you do not have to know the pressure and the fracture half length in order to do this method. Matter of fact, once you do the method, it then tells you what the estimated half length and permeability are.
Yeah, I think the quick answer is these things here, the tau and the gas in place. Remember how much and how fast, or what the fitting is done on. Those things that you were talking about are inferred from the fitting.
Yeah, like this seems kind of analogous to someone who skips potentially like, you know, diagnostics and just goes straight to a numerical model, but this is an automatic process, you know, and an alternative that's fast and practical.
Correct.
That seems the case.
That's the answer.
In fact, there are times now I'm slopping back into the CRM conventional world. There are times when I wonder why we get so hung up on permeability, because it's things like time constant and volume that you know, that are the fitting parameters, and those kind of like the bare minimum description of production. How much, how fast. But we're used to it. A lot of measurements of permeability, and everybody is familiar with it. So we'll stay with it.
Okay. Another question is, as far as I understand, the method applies to single phase, slightly compressible flow. If so, then why not use rate pressure deconvolution to generate QUP, whatever QUP is?
Yeah, I think we do. It's that's what I skipped over. That's part of
Okay.
the things that can have the equations out, but that's not the only thing. So we do have that.
Yes, I mean, we are using, this method is based on convolution and deconvolution.
And it is correct that applies for single phase flow, but we also apply it for shale gas wells. So it's a slight modification with pseudo pressure and pseudo variable. So it applies for slightly compressible, but also compressible. The single phase assumption is correct, right? And why we don't use deconvolution? Essentially, your deconvolved solution is your decline curve model. That is your constant pressure solution, and we are using convolution and deconvolution to match to do the history match and to correct the initial and flowing pressure estimates.
Thank you. One of the requests, and maybe Leo or Mark, you can do this, is someone was just asking if the link for the Rapid RTA site could be kind of pasted in the chat window here. If you get a chance to do that, please.
Yes, I am pasting the link on the chat.
Perfect. Thank you very much. Okay, so Claudio has the questions. How does the method work with real tight oil wells with 10 to 20 hydraulic fractures? Have you had a chance to test it?
Well, probably we have. I've only shown a few cases here, but they're realistic data. They're SP data. So I don't see any particular reason why it wouldn't work. So I think yes is the answer.
Mm-hmm.
Yes, we have tested, for many tight oil and shale gas wells. You can select them all you want. You can do analytical RTA model. You can do ARBS, logistic growth, whatever. The decline curve can be empirical or physics-based. It works well. It history match and gives you the parameter accounting with the pressure.
Okay. The next question is, are you planning to add boundary conditions to the method? And I think that would probably include things like no flow boundaries and stuff like that.
Well, the physical-based model has it in there. It has the boundary conditions and things like that. And I said earlier that we are freed from the tyranny of reading the flow. We are not using a full-blown numerical simulator, so it's pretty simple. The boundary conditions is just flow at the external boundary. I don't think the ARBS curves require boundary conditions.
Yeah.
Essentially, your boundary conditions are imbibed in your model. If you are using a model that only sees transient flow, there is no boundary conditions. If you are using this analytical an RTA model for tide oil that we show, you have a transient period and then you have a boundary dominated period. It just depends on the model that you are using.
Right. If you wanted to use a more detailed model, like a segmented model that has 3 different flow regimes, that type of empirical model, you could also apply the method to that. It would work.
Right. Kind of assuming different model geometries. The other question is, are you planning to integrate this method with the CRM technology? And I've never heard CRM referred to reservoir engineering, so maybe you guys can enlighten me if you know.
It's a capacitance resistance model. It's kind of a precursor to this, but basically electrical circuit analog, so it fits for water flooding. And so the fluctuations in the water injection rate translate into fluctuations in production rate. And so you have something that's analogous to the volume parameter, how much the pore volume, and analogous to the pressure of the connectivities between injectors and production. We have several public. If you'd like papers, so please send me an email.
Yes, the only thing I'm not an expert on CRM, but CRM takes into account the pressures, and we can also, and the idea we were thinking about is to incorporate this bottom hole pressure correction and initial pressure correction to that scheme. So that will greatly enhance your CRM history match using this kind of approach.
Okay. Another question is, are you using pseudo pressure in the gas case? I did hear you guys refer to pseudo pressure, but I can't remember if it was for gas or for compressible oil.
It's the gas. Yes, we are.
Yes,
Okay.
that is correct. All the scheme, instead of doing with pressures, we are treating all the scheme in pseudo variables and then coming back to the pressure space. That is correct.
Excellent. Was there any blind validation testing performed, and were the percentage errors compared on that?
I guess I don't know what the question means by blind validation.
Right, because a lot of this work was kind of like based on synthetic, or some of it was synthetic, models where you knew the answer in advance, right? So you could remove some of the history and apply the method and then see how it compared to the known answer, right?
Yeah, I'll let Leo. Yeah, we've done that. Yeah. Mm-hmm. And we just did. I think we just did one case here. It was synthetic. The other were actual data.
Right, from that SB data repository, I think.
Yeah.
Yeah, I think he's mentioning like doing some kind of time cross-validation technique. Of course, you can do that, but you need to know like if your well is entering into boundary dominated flow, and also for doing I would say the hindcast or the time cross-validation, you will need to know your flowing pressure in the future.
Right. I have this is more of an observation, like about 11 years ago at Fiquet, an engineer, Samantha Anderson, she wrote a paper called Pressure Normalized Decline Curve Analysis. And I've kind of pasted the link in here, but it turns out it wasn't reliable for as many scenarios or fluid situations as what you guys have done. So what I'm seeing here is much more rigorous than that approach that we tried 11 years ago. So I'm excited to see a lot of progress on this approach, because the more practical we can get while staying reliable is just a win for everybody.
Right. Good.
Yeah, thank you for your comment. And we based on, this is not our work, it's based on, as you said, Dave Anderson, Tom Blasingame, Bill Hanilk, we just, they were the inspirations of this work and many others that I am not remembering now. Mustafa Anur also as well. they are kind of setting the basis for this improvement.
Wonderful. I don't see any more questions, and so we're kind of approaching the top of the hour. So I'll give our presenters an opportunity if they want to offer any wrap up. But everyone will be getting a link to this recording. I want to thank our presenters for their time and contributions, and everyone for joining this morning.
Thanks, Graham. I'm going to sign off. That's good. You did a great job.
Thank you very much, and thank you for the opportunity of showcasing this work to you and to all the Whitson people. Thank you.
Yes, thank you very much, Graham. And if people have questions, we invite your feedback. Please contact us at the university or the Bureau of Economic Geology, and we invite your feedback. It helps us.
Wonderful. I'll put all of your emails in the follow-up to our registrants, if that's okay.
That's fine. Thanks, Graham. I'm setting up. Okay.
Thank you.
Bye.
Okay, got it there. Okay, good.